And there still have two derivatives in the first term. So today we are going to solve this heat equation under the constant coordinate, spherical coordinate, and the cylinder coordinate. Okay, so just a reminder a little bit, just in case you didn't work on the online material. So last Friday we covered the boundary condition and initial condition of the heat conduction equation. So the first assumption is in this case we don't have any heat generation. Then the equation will become two derivative. Then you need two boundary conditions to solve the x. And on the right hand side, in terms of the steady state, the steady state or unsteady. In terms of the time, then you need an initial condition of the time to solve it. So we introduced several conditions. For example, the first one is the retreat condition, which means you know the temperature on the surface. Then you can easily plot the boundary condition 指定表面的温度 the retreat condition. And the second one is Newman condition, which means I know the heat flux on the surface. 指定表面热通量的 the case. For example, you have something heat up on the electric stove, then that will be the case. Then we will introduce an example on the textbook later. And the third one is we have an insulated wall. 有一边是绝热的状况. Then the maximum temperature will be appear on the surface. Okay. And the fourth is the Robic condition, which means you have the convection on the one side or two sides of your wall. So the conduction will equals to the amount of the heat using conduction to transfer will equals to the heat you transfer using the convection mechanism. Okay. And then we also describe a little bit further with the one with the asymmetric condition. Then usually in this case there will be the heat generation in the middle. Then we will cover in the 2.6 section, but not cover in this midterm. So don't worry about that. Then besides that, we also mentioned the perfect contact surface and the imperfect surface. Then this will be the next chapter, chapter 3, because we're going to introduce the resistance, the thermal resistance to describe if there's an imperfect surface, then do we have a parameter, then we can describe how the heat, how difficult the heat going to propagate along the different cross-section. Okay, so that will be the boundary condition and initial condition ideas of the heat equation. Now we're going to apply those stuff in the different coordinate. So before that, we need to give them a little bit assumption. So today we are going to cover constant and also the cylinder and also spherical. But because we want to eliminate the variable, so we are going to discuss only steady state and one dimension. So in the constant, we only describe something in the x direction, and in the cylinder, we describe something along the r, and as well in the spherical, it's also r. Otherwise, we discuss zeta and the z position, but now we only focus r. So before that, we give some assumption. So the first assumption is one dimension, which means the heat is going to propagate along one direction. And the second one is this should be the steady state. Then in this kind, we can get rid of the term on the right hand side, which is involve the time. And the third, then there's no heat generation. So without heat generation, okay. 不具热源的 Okay, the fourth, then we assume the constant of K. So, 热传导系数我们设定它 constant. So which means we can take out the K from the equation. It's no longer in the derivative term. Okay, and the fifth, that's a big trigger one. It's not normal. The surface area, the area is constant. So the area that he's going to propagate will be constant. So in the upon case, you probably think, although the area are always constant, but in some of the case, in case of its nozzle or diffuser, then in that case the area will change. 喷嘴或是扩散器，在这个 case 当中，你的热传，例如说喷嘴，是从很大到很小，再很大。In that case, the area will change. So we are not going to discuss this case in this section. Okay, so there's 5 assumptions before we are moved into the material today. So now again, we write down the governing equation. Then you probably can get a hint. This will be a quite important equation you need to remember. Okay. Okay, let's just write it down. Sorry. Okay, this is our governing equation. So based on the assumption we just made, for example, this is one dimension, so we can get rid of this. And this is also, and also this. And this is first one, the first assumption. And we also mentioned this should be steady state, so the time term is also get rid of it. And no heat generation, this will be number 3. And we move down the K, so this will be number 4. Okay, so based on those assumptions, we can simplify our equation into only one derivative, second derivative, and the right hand side will become 0. Okay, let's go through a bit again. So based on those 5 assumptions, we can conclude our governing equation of the heat conduction into this simple one. So this will be the second derivative of the temperature. Oh, sorry, that will be R. My mistake. Okay. Then if we want to discuss in the xy coordinate, then we will need to change the R into X. So this will become like this. Okay, when you see this equation, any equation after second derivative equals to 0, what does it indicate? It indicates the temperature distribution along the distance will be linear. 好，任何经过二阶导数的参数，它还是线性，它还等于0，那就表示它的参数一定是线性。So if you just do second integration, then the Tx should be C1x plus C2. Then this is linear, okay? 好，如果你不相信的话，做一下2次积分 ，equation 就长这个样子，这最基本的。Okay. So then we can start the coordinate, and we have a wall here. Then T1, T2. And because we know the mystery of the mass, so now we already know the temperature distribution or temperature profile inside of the solid should be linear. Either the slope is positive or negative. Just assume now is in this direction. Okay. 好，我们就会确定它里面的 temperature distribution 一定会是线性的。好，那它是往上往下是不一定，看题目怎么告诉你，但至少你知道它的 distribution 一定是线性的。So when it becomes the linear, then the boundary condition and initial condition is relatively easy. So let us write it down again. So the governing equation now, the governing equation will be, let's take a part of the second derivative and we write it down like this. 我们把它拆开来。Okay, then when we do the first derivative integrate, it will become C1. And when we do the second, then we got the equation we want. Okay. 好，我们刚刚已经写在上面了哦，从这边来，所以这个就是我的 temperature profile， 在这个 study 里面的 temperature profile。Okay, then we apply the boundary condition. What's the boundary condition? When the x equals to 0, then the temperature equals to T1. When the x equals to L, or the thickness of the material, then T will equals to T2. That's the boundary condition. So when we put those boundary condition inside to our governing equation, then we will find the T1 will equals to T2. Then the T2 will equal to T1, constant 1, L plus T1. 好，把它带回原本的公式当中。First we put the x equal to 0, then we got the T1 equals to C2. Then put the C2 back to the equation, and we got what? T2. Then we have the constant coordinate temperature profile. Then we run this a little bit. Oh, T1. Okay. So this we'll call the temperature distribution or temperature profile in the constant coordinate. Okay, so in this chapter we're curious about two things. What's the temperature profile and how many heat rate is going to transfer? So the second one will be what's the heat rate? Let me write it down at this part. Okay. 好，另外一个我们在意的是 heat rate, heat flux. So what is the heat flux? So the Q, we're using the Fourier law, partial, not partial. This is one dimension. Sorry. You can write it down like this. Okay, then dt dx, then we can put it down like this. The dt means the T2 minus T1. Then the dx means the thickness of the material. And that's it. But if you want to slightly organize the equation, you can take it out parameter, then put a negative term inside, then will be T1 minus T2. And this function we call thermal conductance. I write it down. Sorry. Thermal conductance. Usually in the textbook it will written as a C star. 这个叫做热导介质系数。So it's kind of unified a little bit. It's how the heat going to transport. So you can write it down like this. The Q will equal to C star and delta C T. 好，就是这个东西的热传，这个 heat flux 啊，等于这个 thermal conductance 乘上两个 surface 之间的温度差。好，这是一个比较简化的说法。你如果不需要整理的话，那我们就停留在上面就好了。OK。好 ，So in the section 2.5, we only care about two things: the temperature profile and the heat flux. How can we calculate? So this is a constant coordinate. Okay? Then if we have time, we will do the dimensionless analysis. But today we are going to first cover 3 different circumstances, and then we will go back. Okay, so now we tackle the constant. Then we move to the cylinder one. Let's move to the cylinder one. Okay. So in the cylinder one, if you remember, the n will equal to 1. So let me write down the equation again. So every time you write it down and try to remember. No heat generation and steady state. Okay. Okay? So now the governing equation, we take it out the k, then it's one dimension and will become dt dr equals to 0. Okay, then we get rid of the term in the front. Then we can do the first integration. Sorry, I should write it down like this. We just integrate the first time, so it will become this. And we get rid of the r, then will be dt dr equals to this. Then we integrate again. Then we got the temperature profile becomes C1 long R plus C2。你的 R 在分母所以你在做一次积分的时候，它就变成 long。Okay, when you see the long, then I hope you remind something quite similar in the fluid dynamic, which means you won't get anything when the R equals to 0。我们绝对不会再求 R 等于0的时候这个地方的值。因为这样子 long 会等于什么 ？Negative infinity。Alright, let me write it down. Because of long 0 equals to minus infinity, so R never equals to 0。我们一定不会去求这个中间这个值。OK。好，这是数学上的一个小提醒。Okay, so let's draw a cylinder like this. Then if there's a thickness and there's a different is A, B. Then if I have a temperature at the inside, we call TA, and the outside we call TB. And what's the temperature profile? And also how much is the heat flux going to transfer either from outside to inside or inside to outside? Okay, so let's write it down the governing equation again, and this are the boundary conditions. So the TR equals to C1 long R plus C2. Then the boundary condition is when R equals to A, then T equals to TA. When R equals to B, then T equals to TB. Easy. Then the equation will become TA and C1 long A plus C2. Then TB equals to C1 long B plus C2. 好，就是把那个 R 用 AB 带进去。 Then we quickly use the TB minus TA, then we will get C1 because we want to get rid of the parameter, to get rid of the C2, so it will become C1 long B divided by A。好 ，long 之间的互减的话，它就会变成分数的形式。Okay. And the C2, then we will know there will be TA minus C1 long A. Then C1 will equal to long A E minus TA. Then the C2, we can also write it down like this, TA minus, long TA, TB minus TA, long A. Okay? Then we'll drive it back to the equation. Then solve it as TR, the temperature distribution, equals to TA plus a very long one. Come on. And then write it down as this. Long TA, TB minus TA, long RA. Those are the temperature distribution in the cylinder coordinate. Okay, so if you don't want to remember the formula, then you can drive it during the midterm if you don't like to remember. It's not that hard, so as long as you know the boundary condition you're going to apply it. 不会太难啦，这都是相对比较简单的二阶导数的推导。Okay. Then how about the Q, the heat flux? So if you guys have finished this page, I'm going to move to the heat flux. Okay. So how about the Q? Then the Q will become, let's write it down again, minus Ka dt dr. Then in that case, minus K, 2 pi L, and L. Then dt dr, what is dt dr? If you remind it, then it will be this one. If you recall, this is here. dt dr equals to C1 divided by R. Come back. Then let's take out those term. Then will become minus C1. Then minus EBTA okay, then the C1, we put the C1 inside here. Then we organize a little bit. OK， 好，它热传量就变成跟你的面积有相关，以及它的长度，长数 k 从内侧的温度减掉外侧的温度，然后下方的分母取 long 的比值。Okay, so those are the Q in the cylinder. Okay, so those circumstances are under one dimension and the area is a constant, okay? So we can take rid of the 2 pi LR and then drive all the stuff. Okay, now we move to the cylinder coordinate, not cylinder, spherical coordinate, okay? Okay, spherical. And you have a ball. Then there's the inside. Then look like this. Then you have a radius A, radius B. Then you have a temperature on the surface called TA, and also here TB. Quite similar with the one in the cylinder coordinate. Then we write it down the governing equation again. So N equals to R, so the K R square dr R square dt dr will equal to 0 because there's no generation and it's steady state. Then we get rid of the constant term, then we write it down like this. Then we integrate again, R square dt dr equals to constant 1. And we divide R square again. Then dt dr will equal to R square C1. You might find the pattern here already. So the TR will again become minus RC1 plus C2. Could you remember how we get it here?积分我们写在这里好了 ，x 的平方 dx 等于 x 的负2次方，这样子就等于负2加1 x 负2加1加 constant， 所以等于负的 x 加 c。Okay, so if you cannot remember how we drive it into here, then those something remind you. Okay. 我们的次方向在后面，然后把它拉成这个样子，然后变成这样子。So again, we apply the boundary condition. The boundary condition when R equals to A, the T equals to TA, R equals to B. T equals to TB, then the C1 will become B minus AB. 我直接写给你，因为这个记没有什么，这个就是带进去而已。 不常用，但是课本有讲，我们还是推一下。Then the Q. And the Q is quite easy. Okay? We put this number here. Then this is the surface area of the spherical ball. Then you got this. 它的 Q 相对来讲简单很多。Okay, so last 2.5 section. Then we move into exercise or example to help you to understand easily. So if you have textbook, you can open it to page 104, or in the PDF file there will be example 2.12 or example number 3 maybe, if I remember the one, this one. Exercise 5. Okay. Okay. So once you finish the note, then we move to the example. Okay? Okay, let's see this example. Okay, we have a heat conduction in the base plate of an iron. So now we consider a base plate of 1200 watt household iron， 就是我们有一个电熨斗。那它这个电熨斗呢，它本身用电阻热感的方式提供了一个1200瓦的 heat flux 在它左手边，但它现在呢，它下面有一个 iron， 有一个 thickness of L equals to 0.5 centimeter 的 iron 在下面，然后 with the area of 300 centimeter cubic square, and the thermal conductivity of that iron K equals to 15. Then the inner surface of the base plate is subject to uniform heat flux generated by the resistance heater inside. 它是用电热阻式的，然后他讲说非常重要几个字他说在 uniform heat flux。OK， 好 ，and the outer surface lost heat to the surrounding temperature at the environment temperature is 20 degrees C by convection, as shown in the right-hand side figure. And take convection heat transfer coefficient to be H equals to 18 blah blah blah. And他说 disregard the heat loss by the radiation. So in this case, we only talk about the conduction and convection. We didn't care about the radiation, and obtain the expression of the variation of the temperature. 其实就是 temperature distribution, and evaluate the temperature at inner and the outer surface. Okay. Some of the students might wonder, Professor, you just talked about 2.5 section is without the heat generator. Why exercise 5 there's a heat going to generate with amount of 1200? OK， 好，这个 case 呢其实是不包含 heat generation 的考虑，所以我们就是把左边把它当成一个均匀的指定表面热通量的 case， 也就是我们在讲 boundary condition 跟 initial condition 的第二个 condition Newman condition。OK， so we consider those stuff is uniform heat flux transfer from the left hand side to right hand side and going to get rid of the heat by the convection。不是铁板本身在发热，是铁板的左手边有一个 heat flux 从左边传到右边。所以这个 case 是不一样的不是 solid 本身在发热， 是 heat flux 从左边传到右边。好 ，so let's take a look how we going to solve it. So first, usually I will roll it down or draw it down what it looks like. So x t. Then we have the thickness of the iron. So I will roll it down like this. For example, like this. And maybe. Okay, then we have the iron. Then according to the question, then you have a uniform heat flux on the left hand side. Then on the right hand side, you have a fixed area, and then there's a convection edge here. And the environment temperature is 20 degrees C. And the thickness of the iron is 0.5. Let's write it down L first. Okay. Okay, just remind you a little bit again. So it's not iron itself has the heat going to generate. It's the constant heat flux from the left hand side to the right hand side. So let's confirm if they fit with our assumption. So we have one dimension, yes, check. Then there's no time difference, so it's steady state, steady. Then third, there's no generation. And the area is fixed. And it also gives you the K. Okay. Fifth. Okay, so this equation fits all the parameter or the criteria we want. Okay, so let's pull out the governing equation again. So now it's a constant coordinate, so it's a second derivative, but it's one dimension. Let's write it down just like this. Okay, so as you remember, there will be C1x plus C2. Okay, heat flux is relatively easy. We solve the heat flux first. So the heat flux equals to Q minus A, then dt dx, where the x equals to 0. Then we put here a number, and this is 300. But be careful with the unit. This is a centimeter, right? So we need to convert the centimeter square into meter square. Okay. Okay, so at the same time, this is what we have on the left-hand side, conduction. 这个. Okay, we can use the Fourier law. Then about the right-hand side, it's about how many heats going to propagate using the convection. So we can write it down like this. So the left-hand side conduction, x then equals to L, will become the H. T equals to L minus environment temperature. Okay. This will be the right-hand side. Then if you recall, this dt dx, this becomes c1, right? We already derived the equation, so let's pull out the equation like this. So the c1 will equals to a minus q, and the c2 will become h. Q, we put it down back to the equation. A q and then we write down here the Tx now will become the environment temperature plus the Q you have L minus X K plus this. So if you want to know the inner surface temperature, then you put X equals to 0. So inner T, then X equals to 0, then outer T, then X equals to L. Okay, so in this case, you just pull out the number inside of it. Okay, so the first challenge, for example, in this example, the first challenge might be something that you need to convert 1,200 watts into the Q. That will be the first one. So Q divided by A, that you got the small q. That's the heat flux you want. And then the other equation using the heat flux. So making sure you didn't pour the 1,200 directly into become into your Q。好，这边你要先把那个系统给的热量换成我的热通量，所以一定是前面要先一个大 Q 去除上我的 area， 然后来的这件事情是我传导从左手边传到右手边蓝色的那面墙的 boundary condition 应该怎么写？的 equation 啊，就是左手边的 equation， 然后右手边就是 conduction 变到 convection， 这个 heat 它怎么传？那这个都是 heat flux， 所以你可以看到这边是没有 A 的，第二个方程式这边是没有 A 的，这个是 heat flux 的部分，然后用这两个方程式呢去求解我的常数 C1 跟 C2。我们现在是先把 general 的 equation 全部写出来给你，所以它的 temperature difference。如果是 Newman condition 的话，会 become the environment temperature 跟你的 heat flux 有关，再跟你的 thickness 跟你的常数 K 跟 H 是有相关的。Then if you want to know， 如果你想要知道墙内侧跟外侧，就是那个 ion 那个熨斗靠电热器内侧跟靠 environment 的温度的话。就把 x 等于0带进去，跟x 点 L 带进去，那就看你的 thickness of the iron 是多厚，然后去做这件事情，可以吗？Okay. Then let us go through another example. Cylinder. So it's quite similar. First one, write it down the general or the governing equation. Okay, derivative, 两次 derivative 在里面的这个 case. Then put out the boundary condition as the question mentioned. 这个呢 case 是一个string 一个 pipe， 好，然后这个 pipe 呢，它想要知道这 steam pipe，what's the heat loss through the string pipe. The length of the string pipe is 20 meter, then inner radius is 6 centimeter, then outer radius is 8 centimeter, and the thermal conductivity of the material is 20, as shown in the right hand side figure, and the inner and outer surface of the pipe maintain the average temperature of temperature 1 and temperature 2. Then obtain the general relation of the temperature distribution, 就是我们说的 T as a function of R, 就是 temperature profile inside the pipe under the steady condition. Then determine the rate of heat loss of the steam through the pipe. 好，一样就是都是讨论 temperature distribution 跟 heat flux 的问题。好 ，start with the governing equation, apply the boundary condition. So at the R1, then you have the T1 150度 C, R2 T2 等于60度 C， 然后把它带进去啊，一次做第一次微分 ，then we got the C1, we already drive the equation. Then we did the second time, then you will got the constant here. And the most important is you will need to remember when the R is below it, then it will become long. 好，这个是公数这个微积分公数应该要记得的。Okay. So then just put out the temperature inside of your equation, then you will got the number. It certainly be easier if you directly remember the equation, but it is not trouble if you want to drive it during the exam or solve the question. 两者其实都不难。你要嘛你可以直接记，或者是你从头做推导，也不是一件很困难的事情。Okay, so far, any questions? Then if you have textbook, there will be another example called heat conduction through the spherical ball, but the concept is the same. It's just repeat the concept, we just drive it in this hour. So it's not much difference. So those are the material we're going to cover on Friday. The material we're going to have the exam. Okay. Any questions? If no, we're going to dismiss slightly earlier because I want to talk something, but it will be take more than 10 minutes. Will delay you guys. 好，清楚的考试有其他问题吗？ There's no other comments on or questions about Friday's first exam? 可以吗？第一次考试的题目都相对来讲，在热传当中是很简单的，方程式也很简单。然后后面我们会有更多的 PDE， 然后甚至是有一些是经验的 PDE， 你要现场查表，那个就会比较难，所以大家把握一下第一次考试都相对来讲是比较简单的题目。Okay, there's no further question. Dismiss the class. The question won't be content with the degeneration. So that would be 0.6